Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology. We have been learning the subject basic electrical engineering, and we have been discussing about the transformer. In our previous session we have discussed about the magnetic materials and BH curve as well as the transformer and their constructions. In our today's session we are going to discuss about the working of transformer and EMF equation. Then we are going to discuss about the ideal transformer, practical transformer, three-phase transformer, and lastly we are going to discuss about the auto transformer. So let us first start with the working of a transformer, where we can already discuss about the transformer. There are two windings, primary and secondary. So once you apply the AC current to the primary winding, there is a generation of magnetic flux in a core, and now because of this production of magnetic flux, that will linked with the secondary winding, and that will also induce EMF in a secondary winding. So this is a basic principle behind the transformer, and that basic principle we define as a electromagnetic induction using the Faraday's law. So here we'll start with when the current in a primary coil changes, being alternate in nature, the changing magnetic field is produced. So here the changing magnetic field gets associated with the secondary through the soft iron core, and because of this, hence the magnetic flux linked with the secondary coil changes, and which induces EMF in a secondary coil. So this is a basic principle behind the transformer, which is based on the electromagnetic induction Faraday's law. So there is a circuit where you can find the symbol where there is a primary winding having the number of turns is N1, there is a secondary winding having the number of turns is N2, right? And throughout this V1 we are going to apply the sinusoidal signal, a complete cycle, and during this complete cycle how the transformer is going to induced EMF in a secondary winding as well as in a primary winding. So that is a complete cycle when you apply the AC signal. So I1 is flowing through the primary winding, so there is a production of magnetic flux. Because of the production of magnetic flux, there is a induction of EMF in a primary winding is defined as a E1, as well as the flux phi is linked with the secondary winding, that will also induce EMF E2. So in our this session we are going to discuss about the derivation of this EMF, induced EMF in a primary winding and induced EMF in a secondary winding. So let us first start here with N1 is nothing but the number of turns in a primary winding, N2 is the number of turns in a secondary winding. Phi m is called the maximum flux in Weber, that is also defined as a maximum flux density multiplied by area, and f is nothing but the frequency in hertz. So once we take the 1/4 cycle of this full cycle, we can find the average rate of change of flux, and that is average rate of change of flux is nothing but the maximum value of flux divided by 1/4 of the frequency. So that is defined as 4 times of frequency with the maximum value of flux in terms of the Weber. Now here the rate of change of flux per turn means the induced EMF in volts is nothing but the average EMF per turn is, that is equal to 4f into phi m volt, right? This is the average value. So we convert this into a RMS value, since the induced EMF is always in RMS value. So here the flux phi varies sinusoidally. So the RMS value of induced EMF is obtained multiplying the average value of the form factor, where the form factor is nothing but the ratio of RMS value to the average value, that is equal to 1.11. We are taking the help of this equation and we'll find the RMS value of EMF per turn, that is equal to 1.11 into 4f into phi m, that is equal to 4.44 f into phi m in volts, right? So now if you take the RMS value of the induced EMF in a whole primary winding, we define as the induced EMF multiplied by number of primary turns, right? So that number of primary turns we define as N1. So my of equation of induced EMF in a primary winding E1 is equal to 4.44 into f into N1 into phi m. Right, so here I can put the value of phi m is like Bm into A. So the equation you can also rewrite like induced EMF in a primary winding E1, that is equal to 4.44 into frequency into number of turns N1 into magnetic flux density, which is a maximum magnetic flux density Bm into area A. Right, same terminology if we apply for induced EMF in a secondary winding, because the whatever magnetic flux is being induced or whatever magnetic flux is being produced in a core, that is also linked with the secondary winding, and that will also induced EMF, and that EMF we also again consider within the same terminology. So here the RMS value of this induced EMF in a secondary winding we define as a E2, and that is E2 is equal to 4.44 into frequency into number of turns of secondary winding N2 into magnetic flux density Bm into area A. Now you have in general total two equations, which here you define as one of the equation E1 is equal to 4.44 into F into N1 into Bm into A, and another equation E2 is equal to 4.44 into F into N2 into Bm into A. Now we are taking the ratio of equation 1 and 2. You can see here E1 by N1 is equal to E2 by N2, and that is equal to 4.44 F into phi m. It means the EMF is same in both the windings. So here you can see the EMF is same in both the winding, where in ideal transformer case where there is no load, in this condition V1 is equal to E1 and E2 is equal to V2. That means the applied voltage V1 is same as the induced voltage E1 in a primary winding. Same way, the induced EMF in a secondary winding E2 is same as voltage V2 which is appeared across the load if there is an ideal transformer, right? So you can find voltage transformation ratio K I define as a E2 by E1 is equal to N2 by N1. Now based on this value of K, I can categorize transformer. Constant K is known as the voltage transformation ratio, where if N2 is greater than N1, that means K is greater than 1. So this particular transformer is called as a step-up transformer. If N2 is less than N1, so K is less than 1, so that transformer is known as the step-down transformer. So from this, if we also write, if we consider this as ideal transformer, and if we find the power consumption from the primary winding as well as a secondary winding, or power derivation from primary winding or secondary winding, P1 is equal to V1 into I1 cos phi, P2 is equal to V2 into I2 cos phi, and if I am taking this two equation and taking the ratio, I can find V1 into I1 is equal to V2 into I2, where both the power factors are same. So from this you can be able to find I2 by I1 is equal to V1 by V2 is equal to 1 by K. Now this particular ratio is also defined as a inverse ratio, which is nothing but the inverse of voltage transformation ratio. This is also defined as a current transformation ratio in terms of the transformer. Now this are the different ratios in transformer. Now let us look about the losses in a transformer, right? So once you apply the voltage, obviously this is a mechanical system and it is made up of the core and winding, so it must have incurred the losses. So there are two types of losses in a transformer, and this is only because of the core and windings. The losses are occurred due to the core is defined as the iron loss, because core is made up of the iron. Same way the losses are occurred due to the windings, it defined as a copper loss, because winding is made up of the copper, right? So once we find the equation of copper loss is nothing but simply the equation of power when I1 square into R1, this is called copper loss in a primary winding, and I2 square into R2, this is called a copper loss in a secondary winding. So copper loss is equal to I1 square into R1 plus I2 square into R2, where I1 is the current which is flowing in a primary winding, I2 is the current which is flowing in a secondary winding, and R1 and R2 are the resistances of primary winding and secondary winding respectively. Same way, if we further discuss about the iron losses, which is again of the core, and core is related with the hysteresis losses and eddy current losses. So there are two separate equations you can see here. WH is equal to N, which is efficiency, into Bm raised to 1.6 into frequency into volt in terms of the watt, and the eddy current losses WE is equal to P into Bm square into F square into T square in terms of the watt. So this is about the losses in a transformer. Now let us discuss about the three-phase transformers very shortly, where in a real life practical situation the generation of three-phase transformer is much cheaper. So almost all major generation and distribution system in the world are the three-phase AC system, where the three-phase transformer plays an important role in this transformer. The three-phase transformers plays a very important role, where it is constructed from three single phase transformer, or another approach is to employ all common core for all three sets of winding of the three phase, right. So the construction of single three phase transformer is preferred today because of it is lighter, smaller, cheaper and slightly more efficient, right. So there is an advantage that each unit in the bank could be replaced individually in event of the fault. However, this does not overweight the other advantage combined with the three phase unit, right. So from this three phase transformer, the three cores are available, where the end part of the limb, there are three separate windings are available with the primary and secondary winding. So by this way you can reduce the middle limb by a single limb, where the central leg can be removed. So how the core of the compact phase shift is built, where the phase magnetic flux generation throughout this three phase transformer is phi A plus phi B plus phi C is equal to 0. So you can easily, here central leg can be removed by this way. So this is a simple construction of the three phase winding, where the outer limb, where you can easily construct the primary and secondary winding, or you can easily wound the primary and secondary winding with this phasor diagram. So now if you check here, there are two construction of the three phase transformer. One is a separate phases of transformer is available, where you have a three separate cores, where in each core you have a primary and secondary winding, right. But in another way, this is a very simplest way, there is only one core instead of three cores, where in each core three limbs there is a primary and secondary winding is available. So this is a much cheaper and easier way of construction of this three phase transformer. Now you can see this in three phase transformer connection, the windings of the primary and secondary in any construction can be connected either in a star shape or Y or a delta shape. So there are four combinations you are going to get in terms of the construction of this winding over a three phase transformer. So one of the cases delta and delta three phase transformer, that means here primary winding is also delta and a secondary winding is also delta. And case number 2 is a Y and Y, that means the primary winding is Y connection and the secondary winding Y connection, or it's a star to star. Same way case number 3 is Y to delta, and case number 4 is delta to Y. So you can further discuss about the connection of this Y and delta connection. You can check here, primary winding is made up of the Y connection, which is a star connection, and the secondary winding within a same limb is defined as a delta connection. So this particular terminology you can define as a Y and delta connection. So this upper circuit and lower circuit both reflect the same as Y and delta. But if you talk about the case of delta and delta connection, where both the primary and secondary winding are connected in a delta shape, right, both are connected in a delta connection, right. So same way, if you further discuss about all four possibilities, where first case is a delta to delta, where primary and secondary winding both shapes are the delta and delta. Case number 2 is a Y and Y, where primary and secondary both are star connection or a Y connection. Case number 3 is Y to delta, where primary winding is a star connected and secondary winding is a delta connection. And fourth case is a delta to Y, is primary connection is a delta and the secondary connection is a Y or star. So here conversion also possible using the factor of 3 and 1 by 3. This is like same as a star and delta, right. So this, thank you dear students. If you have any doubt, please write in a comment box. Thank you very much.